Welcome to the Crazy Hat Chemist, so another video on gases. Bam! Alright, today we're having a cold problem here today. Very cold problem. So 1112 tetrafluoroethane, which is HFC-134A. And the formula for this is CH2FCF3. It has a molar mass of 102.3 grams per mole. It is used as a refrigerant instead of Freon, because it is less depleting than Freon to the ozone layer. Okay? You want to maintain your refrigerator at a normal temperature, of which is 4 degrees Celsius, and your freezer at negative 18 degrees Celsius. A compressor maintains 500 psi, which is 25,858 torr, and contains 4.32 kilograms of this tetrafluoroethane as a refrigerant is used for this. What volume of air is expelled into the refrigerator to maintain normal operating temperature of the refrigerator or the freezer? All right, so let's figure this one out. This is a super cool problem. Huh. It's a cool problem. Get that? Huh? Okay. All right. How much air would be necessary for the freezer as well, of course? All right. So PV equals nRT. That's the ideal gas law. That's P for pressure, V for volume, N for number of moles, and R for the gas constant, T for the temperature. Okay, I'm rearranging this to solve for volume. So I've divided both sides by P. Now I get V is equal to nRT divided by P. You should have seen this when I derived the ideal gas law, just like that. Okay, and then what I'm going to do is I'm going to convert this mass into moles, because I need to plug into the ideal gas law. So I got 4.32 kilograms of the refrigerant, and I'm going to convert that into grams using 1 kilogram and 1,000 grams, and then using the molar mass so that I cancel out grams and I got moles. So I got 42.3 moles of that refrigerant. Okay, now I'm going to convert the 25,858 torr into atmospheres. Okay, and I've done that right there with 760 torr and 1 atmosphere. And again, my units here of moles, the amount of gas, and atmospheres for the pressure need to be in those particular units, because the gas constant is in liters, atmospheres, moles, Kelvin. So that's why I'm using that. Now, one more thing I need to do is I need to convert my temperature as is appropriate. And for the refrigerator, I'm going to take the 4 degrees Celsius and convert that into Kelvin, and that would be 277.2 Kelvin. I'm going to plug this into that equation, which is a rearrangement of the ideal gas law to solve for the volume, and this is what I get. I got 42.3 moles times the gas constant, 0.0821 liters, atmospheres, moles, Kelvin, times the temperature, 277.2, divided by the 34.0 atmospheres. And that is going to give me a volume of that refrigerant, of that air that's being expelled into that refrigerator, of 28.3 liters. Okay, now I'm going to do a very similar thing, except I'm going to use the freezer as an example. Okay, and now my temperature conversion is right here for the negative 18 degrees Celsius. That converts to 255.2 Kelvin. I'm going to now substitute that 255.2 Kelvin instead of the 277.2. The amount of moles of refrigerant is still the same. The gas constant is still the same. And the pressure is still the same. And I'm going to get a volume here now for the freezer. And that volume for the freezer is 26.1 liters. Okay, hopefully that worked out well for you. That is a cold problem, and don't be so cold. Okay, so, and here are some notes on this. So a note on the cold problem. So how does a refrigerator or a freezer actually work? So coolant gas is compressed, causing the temperature to increase. The hot gases pass through a radiator, allowing the excess heat to escape to the environment. Okay. And then the gas is pumped into the refrigerator or the freezer, as is the case. As the gas expands in the refrigerator or the freezer, excuse me, it cools off and heat is drawn from the interior of the refrigerator. That is how a refrigerator or a freezer works. Super cold. Okay? Don't be cold. Subscribe to my YouTube channel. Give me a thumbs up, and don't be cold. See you next time. Bye now.